This is going to be the lecture about the surface integral of a vector field over S. So let me first give you a motivational question. First, we're going to introduce this idea of a number density vector of molecules per unit area per second. When we usually say density vector, when we just say density like this, we always think it's a scalar, but this is different, it's a density vector. So we have to explain the meaning of this vector. The first bit is about the meaning of the magnitude of this vector. This is going to be number density as a scalar on the region that is perpendicular to F and per second. Okay, let me use a picture to explain that. Okay, what I mean by this region perpendicular to F is this vector, for example, is pointing this way, and we're going to sample nice region out there, which could be any shape, but it's perpendicular to this vector F. Let's say the area was this delta A, and number of molecules that went through this region over one period of 1 second is, let's say that was capital N. Then we have this thing, number of molecules, and it's given. This area of this region, delta A, which is perpendicular to this vector F, and we measured it over 1 second. And this number density would be number divided by the area. So that would be the notion of this density. So we have this notion. This magnitude of this vector represent number density. You can think of this as a following situation. Actually, I'm going to use in the next slide kind of actual example that is naturally rises, and then you can at some point you can think about this as a kind of velocity. So if it is moving fast to a certain direction, of course the more molecules will pass through, so that's going to be very directionally proportional to the velocity, so that is representing here. So what about the direction of F? Is the direction of the molecule flow, so that part is natural. So these two things, these two information is put together into this vector form, and that's what we mean by density vector of molecules per unit area. Okay, let me naturally associate this one with the velocity. Think about the flow of water in a two-dimensional way, which is like this. For example, at each point, the flow is the same direction, and the magnitude represent number of molecule. But think about this as a velocity, then that's how fast it's moving. Now, if we introduce this obstacle like rocks around it, and if you put a little plate, let me see if I put a little plate over there and measure how many water molecules are passing through over a given certain period of time, versus over here, because the same kind of volume is kind of put it into a very small space over here, you can see they have to go through fast. So the velocity about that area actually increases, therefore number of molecules going through that portion period of time is getting some more. So if you put the vector, number density vector over there, it would be a lot faster. So we get represented like this. It's a shorter length and then a longer length. That's they are going definitely fast. So because of this obstacle, of course, and over here, of course, the direction of the flow changes as well. So you can kind of tie this number density vector to a velocity if it is, if that makes sense. But you can certainly think of this as air molecules. Then it's going to be, slightly different. That's going to be, actual density occupied in a different space might be different, although that's not usually the case for fluid or liquid. But that's what this is about. So let me introduce the question that we have to focus on. So let me explain this important goal we're going to do. We're going to count the number of particles that is passing through certain surfaces that is inside this situation. So surface here can be curved, and that's the whole point. So here's how we're going to do it. All right, I want you to, here's the situation. We're looking at a certain position, and then this is very, very small scale. So this vector, the number density vector in that position is kind of constant. We're looking at a very small region, and there's this imaginary plate that is a rectangular shape. it has area delta A, let's say. And let's think about how many particles are going through over 1 second here. Because it's area and this absolute value, the magnitude represent the density, if you multiply these two, that's the number of particle per second, if you like. So that's the number of particles that passing through per second. So what we're going to do, we're going to count the number of particles that's passing through over this region. That is actually the same. So we can look at in a slightly different way. So that number is the same, but we're going to kind of calculate the number density as a scalar on this plate here. The numbers are not changing, but it is the molecules that are going through, the area of the region is a slightly different. So that's what we're about to calculate. So I want you to focus on this right triangle that is on this side. Okay, I sketched it here, so that right triangle, and the angle in between there is a theta. If I call this side L, and that side definitely here, using the trigonometry, is L over cosine theta. Okay, I moved that a little bit up here so that it can show what's written is L over cosine theta. Rest of the part is just a cylindrical shape, therefore this length relationship is the ratio of this area of this delta A over here. So if I call that slanted part delta S, and this is delta A, the ratio must be delta A divided by cosine theta. So the area of this one is going to be delta A times the cosine theta. So what we're going to do, we're going to calculate the density on this plate here as a scalar, which is written over here. Density on that part is that this is number of particle, and that's area. This number of particles going through, so they cancel and becomes this absolute value of F cosine theta. You've seen this is a part of the dot product, so we're going to relate this one into a dot product formulation. Alright, let's take a look at this picture first. So that's the triangle copied there. Remember, that was this, if you're looking at it from the side, so that was delta A side. So that's the situation. We don't see the quite area become from the side, but that's where things were, and the vector F is pointing that way. And the absolute value of F times the cosine theta arises as a dot, some sort of dot product form. So I looked at this vector N, which is perpendicular vector, this plate that you don't quite see, but that's a perpendicular vector. So if you parallel transport that up to that position, here's a theta, that's a 90 degree, so that angle right there must be theta, this across must be theta. So angle between F and N, the two vectors, is exactly theta. Therefore this F cosine theta is exactly arises a dot product of these two vectors. So summarize it here. F and N, if you look at these two vectors and if you dot it, there's this formula, the magnitude, product of the magnitude times the cosine theta. So if you choose this N to be the unit normal vector, so that says equals 1, then this formula just becomes this one, and that captures this density on this plate S. So now the density is neatly formulated, which is F dot N. Okay, so density in F dot N, and our goal, remember, was counting number of particles that is passing through the surface S, and this density on that surface is an important information. Let's also get used to the following picture. That is the plate. It is part of, let's say it's a part of the surface S, and it happened that the number density vector is going toward not necessarily the perpendicular, is going through different directions. And what we want is the density applied on an S. It turns out the calculation is that density right there is F dot N. So if you project this vector down to N, which is a unit normal vector, then the magnitude of that picks up the right density. Alright, that's a neat idea. So at the pack of information, it's information that packed into this vector, and this dot product still captures in useful information in this setting. So here's what we wanted to compute. If you look at this as a kj, and if you have a parameterization and use the two parameters, and they're in this situation, and then number of particles that pass through this area per second will be this dot product that measures the number of particles there times the delta sk. So at this point, let me point out this one is actually the component part because we're using this unit tangent vector. Remember, this component part is not just magnitude, it's actually signed magnitude, so that this might pick up negative number. So let's think about what that means. Is that if we happen to choose this normal vector, remember this is our choice actually if we think about it, and this is the given information, and to calculate the number of particles here we chose this vector n in one direction, but if someone else could have been chosen the other direction, and if we're disoriented it's unclear which one we should choose. So it turns out this has to be our choice. So given an entire global object S, the big S, then it has to be, we have to have this consistent normal vector, unit normal vector around the surface. Then we can calculate and we can interpret the meaning correctly. So for example, obviously total number of molecules that passes through across this region is density times the area. We add up all this. But this one turns out to be possibly positive and negative. And over in a certain part of the region, let me draw that picture. Suppose this is our global object and the surface, and then we happen to look at this one. It's a very tiny sample here, and you can look at it other places, and on over here the F might be going out. So a more complicated picture. Suppose we have all this in and out, this crazy number density vector. So overall what this can be interpreted as that if we happen to have n to be in a certain direction, suppose we chose n into this direction here, then the meaning of this one, if it turns out to be negative, it's just an example, then it means net number of particles that pass through from the bottom to top, because that it's our direction of n, is negative. So more molecules actually top to bottom flow as a net calculation. Locally, if you look at just very small, it's always the same direction. So it means more, but globally what this means is this one with the sign attached to it. So interpreting the meaning of this one, therefore rely on your choice of normal vector, unit normal vector of your S. So let me formulate our integral formulation. I showed the Riemann sum formulation before, but you can just put that into this surface integral, and the scalar quantity that we're integrating is this f dot n. Again, n is our choice for f, this surface S, and then because of the choice we say it's oriented surface. If we have surface S like this, and then we have this consistent normal vector, unit normal vector defined on it here. So if I look at this picture, it's not puzzling at all. We can just decide, okay, this is the side, and these, so that's kind of can be defined as an outward direction, but it's our choice again. But there can be a complicated shape such that defining this unit normal vector on the surface is not possible. So the Mobius strip is an example. So let me show you that. So for example, this is a picture available from internet, and if this is created by taking the usual strip and twist it and connect it. If you look at the usual strip, it has a clearly notion of left to right and up and down, but as you twist it and you're connecting it inside and out together, and then it's totally confused. You can start it here pointing this way, so pointing this way, but if you follow through and carefully and come back down here in completely opposite way. So every side must have a, the sign is pointing this way, but if you follow through and then when you come back and it's pointing opposite side. So there's no way to consistently define this unit normal tangent vector. So what has happened here is that using the integral and has the meaning that is no meaning to us. So let me go back to the integral formulation. So if it is simple as like this, and then we have a clearly meaning if this is the positive, that the more particle pass through from this side to that side. If it is negative, and more particle move from that side to that side, that's the meaning of this whole thing. But if it is a Mobius strip that I'd showed it before, and we can still calculate by losing a little strip over there, for example. So for this one, you can lose just this bit here, and if I lose just a little bit of it here, we're not quite losing the information. The number of particles went through that part is almost zero because it's this thin strip. If we lose that, we have this n defined everywhere. There's no conflict or anything, so we can kind of calculate the integral here. The trouble is that meaning of this integral is if it's a positive, what does that mean? It's going from this side to that side. Locally it makes sense, or globally, because we don't have a notion of, still without even missing it, clear notion of how much is going out, in and out. The globally, that integral is kind of confusing interpretation. But if it is just from here to there, we have inside and outside notion, so integral clearly means something. So to have a clear meaning and to avoid the confusion, we only consider the surface integral of a vector field only for oriented surface. So remember, when we consider the line integral of a vector field, we have a oriented path, and also line integral, surface integral of a vector field, we also have to consider this oriented surface. It's all because we're integrating dot product. This is orientation sensitive. So this is an important example. For example, if E is electric field, so you can interpret as a number density vector of electrons, how many electrons are passing through. That's exactly going to be the charge, the Coulomb in the units. Suppose we're looking at this surface S, which is a sphere, and we have a parameterization. Let's say if we have a parameterization, it naturally introduces this unit normal vector. So if you have a parameterization and you have to sample one of the points, see which way it's actually pointing out, and then you figure out, okay, it's outward and inward. All right, once you have a parameterization that is pointing outward like this, or if you want to change it, you can change it. We'll see it later, but understand if parameterization comes with this orientation. Then computing this surface integral of a vector field n will be the how many electrons are going outside or inside or something like that. So this will measure the net charge captured inside this surface sphere S. So if this is a positive, that means because this n is going outward, more electrons are going outside than coming in under this vector field. The vector field is constant, flow into this area, and if this is positive again, it means more electrons escaping than entering under this vector field. If it has to be the same, that's going to turn out 0, because same electron going in and out, and this is important formulation in electromagnetism. So how are we going to calculate it? Is there something nice just like the line integral, and the same phenomenon happens? This is the formulation, where this is the density multiplied by the area, so we capture the total number of molecules that's going through. And with the parameterization, therefore it comes with the orientation, it's going to be R like this. It's a flat piece. Here is a flat piece, and this Jacobian factor that matches this curved piece of area goes like this. And what about this n? Using this parameterization, we can replace it with this cross product. So I added a picture here. This is surface S, and at one point, if you parameterize it, it introduces a U curve and a V curve. The partial derivative of the parameterization correspond to velocity vector along the U curve and a V curve. So clearly it's kind of tangent to the surface, and if you do the cross product, it is pointing to the parallel or opposite of the normal vector. So it nicely introduces normal vector. As long as it's never 0, and you will have normal vector everywhere, unit normal vector, because it's non-zero, you can always define this vector like this. So that n is replaced by this formula as soon as we have a nice parameterization. And then you can see this nicely cancel. This absolute value leaves us just a nice formula where there's no absolute values. So here's the whole formula. If you cancel these things, and you're only left with the cross product of the partial derivative. That's not too bad, although it involves calculated. At least there's no square root. So this is pretty friendly formulation. And this depends on, this notation uses parameterization. So they wanted to introduce parameterization-free notation that doesn't even use this n. So they introduced this notation f dotted with this ds. And they typesetted this part with a boldface s, but on the board it's difficult to do that. So I use this curly s, but that's indicate surface integral of a vector field. So let me remind you of the line integral of a vector field. It was denoted like this, and I think they try to imitate this notation, but this is what's really happening. So it's kind of awkward notation, but I think they try to imitate this line integral of a vector field notation. So let's look at some examples. Sorry, this is a little bit fuzzy picture here. Let me move on to the next one quickly. So vector field is given by this formula. Every position in three-dimensional space, we have this number density vector of molecules associated to it. The surface is closed surface. So S1, the top part, is given by this elliptic paraboloid. Bottom is equal 0, the flat plane. So we're calculating this surface integral of a vector field that will measure the net number of molecules in and out. So I focused on the S1 part first. I looked at this one. This is already solved for Z. Therefore, the parameterization, there's an obvious parameterization. X is going to be U and Y is going to be V, and write it down like this. So once you have it like this, and then this normal vector that RU, RV, we have to understand which way our parameterization is pointing. So I'm showing a little bit more, and this is the standard part. I did not show in this part, so let me write down here. So if you parameterize x and y with the u and v, and we have this parametric equation, if you go through this RU cross RV, turns out it's always this. Okay, so if you differentiate this one with respect to u, and it's negative 2u, and there's negative, so it's 2u, and it turns out 2v, and then it's 1. So we have this kind of, this will be never a zero vector because there's always 1, so that's nice parameterization. So we have to sample one point, just say it's like this one, at 0, 0, 1, where it corresponds to u equals and v equals a 0. So if you plug it in there, the vector is a 0, 0, 1. But you also have to look at the position here. So this, let me write that. It happened that this case is two vectors are the same, but you have to distinguish. This one will give you the point of application, and that will give you the normal vector. So I wrote it in. This one we have to calculate both. This one will be the point of application, normal vector. It's a sample, anything that you can calculate easily. For example, u equals 0 and y equals v equals 0. That's happened to be one of the points there. Then that gives you this point of application 0, 0, 1, 0, 0, and gives you 1. And if you plug it in here, also gives you 0, 0, 1. So it's at that point 0, 0, 1 is pointing upward like this. It happened that this one at that point has length 1, so it is actually the unit normal vector. So we have this one. Everywhere else must be in this direction. So that's S1 with this parameterization have this outward kind of orientation. And the trick is that you have to keep that orientation for the bottom piece all around in the same direction. So I hope it's clear that for the bottom part we have to go below, like this. So I added a few vectors like that. I think this is clear. So how we're going to parameterize this one is the bottom flat part. So x and y will be simply free, and then z is going to be 0, right? So let me show you that part. Alright, let me show you this part, S2 part here. So natural parameterization, of course, is x and y is u, and z is always 0, u, v, and z equals 0. So if you follow that formula that I showed you, the z, partials of z is both constants, 0, 0, and always 1. So this one is a unit normal vector again, but if you go there and then sketch this one, is actually pointing upward. So we want a parameterization that's pointing downward. Whenever this one happens, the trick is that if you swap this u and v, it'll do the job. As soon as you swap this u and v, you cannot use the formula I showed you before. You actually have to calculate RU cross RV. So let me show you on that part. So if you actually differentiate with this x, y, z, and u and v are swapped, and if you look at RU and RV, then this 1 appeared in a slightly different place. If you do the cross product, it actually does pick up -1 there. So this technique always, where you have a parameterization, if it is pointing the wrong way, just simply swap this u and v. It'll definitely change the order, the orientation backward. So it'll always take care of it. So we got this one with this parameterization. If we integrate, and then it's going to work. So here's the final bit of the problem. The surface integral S, which consists of 2 parts, and you have to separate it S1 and S2, that carries the correct consistent orientation from part to part. And S1 has now become a plain, flat double integral, so which is F dotted with the RU cross RV. For that S1 portion, it was 2U 2V1. And R2, and it's for S2, it switches to flat integral, double integral. So that uses this RU/RV, which is 0, 0, -1, downward direction. Okay, so you have to calculate these two and go back to the F, and the rest of the part, it's a straightforward calculation. But you have to think about what this R1 and R2 is, and this is really the X and Y, and because we parameterize X and Y with a U and V, so both of the region, and R1 was a unit circle and R2 was a unit circle. So from here, standard polar parameterization will work. So use R cosine theta and R sine theta for U and V. Here at this point in the double integral, that orientation is not important. If U being this one and V being that one, that'll actually result in exactly the same answer, because we're always multiplying the positive R as a Jacobian for the double integral. So I wrote it down the final bit. The surface integral of this vector field is broken into this 2 double integral as we use the parameterization. It's a y, x, z was the vector field. So if you look at the R1, let me show you the parameterization of R1. So here, x was uv1 minus u squared v squared. That's the parameterization used here. And when you rewrite this one, you have to use its own parameterization. Remember we swapped this uv so that it's consistent with the orientation there. So y is this time just u, and x here is a v, so v goes there, and z here is a 0. But this orientation, unit normal vector happens to be 0, 0, -1, so the dot product is just 0. So we only pick up just R1 part here, which is this one. So from here, R1 came from the circular region, so it's just a polar system. So that everything is replaced with R cosine theta and R sine theta, and there's a Jacobian from the polar change of variables, and that's it.